Imagine you are floating at the ocean's surface. The sun is blazing overhead, waves sparkle, and everything feels familiar. Fish look like fish. Water feels like water. You could almost forget that beneath you lies the largest living space on the planet. Then you start sinking. Slowly at first, like an elevator ride you did not mean to take. The light softens, blues deepen, reds vanish, the warmth slips away. And somewhere between comfort and curiosity, the ocean quietly reminds you that you are leaving the human-approved section. If this slow journey into the midwater abyss helps you relax tonight, please like the video, subscribe to the Deep Sea Documentary channel, and leave a comment sharing when and where you're listening, so this gentle exploration of ocean life can reach more people who fall asleep to science. This is the descent into the midwater, the zone that begins just below where sunlight feels confident and stretches down into a world where light becomes a rumor. It is not dramatic like crashing into the seafloor, and it is not cozy like coral reefs. It is open, empty-looking, and deceptively calm, like standing in a dark parking lot at night and realizing you are not alone. As you sink, sunlight thins out, not all at once, but gradually, as if someone is slowly dimming a cosmic light switch. Colors peel away in layers. Reds are the first to go, then oranges, then yellows, until everything turns a cool, eternal blue. This fading light is not just a visual change. It is a deadline. Any creature living here has to make peace with the fact that shadows rule, outlines blur, and visibility is always limited. If you are hoping to stand out, this is the wrong neighborhood. Pressure begins to build as well, not in a dramatic, crushing way yet, but enough to remind every cell in your body that water is heavy, and the ocean never forgets how much of it is sitting above you. Every 10 meters adds more weight. The deeper you go, the more the ocean leans in, like it is reading over your shoulder. Down here, evolution has had to solve problems that surface animals never think about, like how to exist without air pockets, rigid bones, or the luxury of ignoring physics. And this is where things start getting weird, but weird in a quiet, confident way. The midwater is not loud about its strangeness. There are no reefs bursting with colour, or dramatic predators charging through the frame. Instead, life here drifts, hovers, waits. It is a world where motion is measured, where energy is precious, and where unnecessary effort is basically a bad financial decision. The emptiness itself is part of the challenge. There are no rocks to hide behind, no plants to blend into, no solid ground to orient yourself. It is three-dimensional space in every direction, an endless blue hallway with no walls. For animals, this means nowhere to pin themselves, nowhere to retreat, and nowhere to set up a permanent home. You live where you float, and you float where the water takes you. This creates a particular kind of tension. In the midwater, survival is not about speed alone or strength alone. It is about being subtle, being efficient, being forgettable until the exact moment you cannot be ignored. Predators and prey often look strangely similar at a distance, and that is entirely the point. If everything blends into the same hazy background, then being slightly less noticeable than your neighbour can mean the difference between living another day or becoming an afternoon snack. And while the surface ocean runs on the sun's schedule, the midwater lives in a permanent state of late evening. There is just enough light to suggest shapes, just enough glow to betray movement. It is the kind of lighting that makes everything look suspicious, including you. This dimness has pushed life here towards solutions that feel almost alien, as if these creatures evolved under a completely different set of rules. Because, in a way, they did. The midwater is where the familiar starts to dissolve. Fish stop looking like the fish you recognize. Bodies stretch, flatten, shrink, or balloon. Eyes grow larger or vanish entirely. Mouths become exaggerated, as if designed by someone who was told meals are rare and took that very personally. Nothing here is accidental. Every strange proportion is a compromise with darkness, distance, and scarcity. And yet, despite all of this, the midwater is full of life. It is not empty. It is just subtle. Billions upon billions of organisms drift through this zone every single day, forming living layers that pulse and shift like slow-motion weather systems. You just do not notice them unless you know how to look, or unless one of them decides to notice you first. This is the abyssal in-between, the ocean's long twilight hallway, where sunlight gives up but darkness has not fully claimed the throne. It is a place shaped by constraints, where evolution did not aim for beauty or terror, but for survival under impossible conditions. And as we continue deeper into this realm, we are going to meet the creatures that call it home, each one a quiet testament to how strange life can get when the lights go low and the rules change. To understand the midwater, you first have to forget almost everything your brain associates with the ocean. Forget beaches, forget coral reefs, forget the comforting idea that somewhere below you there is a floor you could theoretically stand on if things got awkward. The midwater is the part of the ocean that exists between worlds. It is not the surface, and it is not the deep sea floor. It is the enormous floating middle, a volume of water so vast that it makes continents look like decorative accessories. This zone stretches across the entire planet, wrapping Earth in a continuous, moving layer of water that connects all oceans into one giant three-dimensional space. There are no landmarks here, no mountains, no trenches, no permanent structures at all, just water extending in every direction. If you were dropped into the midwater with no instruments, there would be no up, no down, no left, no right. Just an infinite blue gradient, and the vague sense that gravity still exists, even if it is being very subtle about it. Because there are no solid boundaries, life in the midwater does not organize itself the way life does on land, or even in shallow seas. There are no neighborhoods, no territories marked by rocks or reefs. Everything floats, drifts, or slowly swims, sharing the same open space. Imagine trying to live your entire life inside a weightless warehouse the size of a planet, where the walls are imaginary and your neighbors are constantly passing through. That is the midwater lifestyle. This openness shapes everything. Without physical structures to cling to, midwater organisms must rely entirely on their own bodies to survive. There is no hiding behind scenery, no attaching yourself to a safe spot. You are your own infrastructure. Your body determines how you move, how you feed, and how you avoid becoming a surprise meal. If your design is inefficient, the midwater is very quick to point that out. The scale of this realm is difficult to overstate. The midwater contains far more living space than all forests, grasslands, and shallow seas combined. It is the largest habitat on Earth by volume, yet it is also one of the least directly observed. Humans tend to explore edges, coastlines, surfaces, solid ground. The midwater, with its lack of scenery and refusal to provide convenient reference points, does not cater to our curiosity. It is not dramatic at first glance, it looks empty, and that illusion has fooled us for centuries. In reality, the midwater is structured in a different way. Instead of physical boundaries, it is shaped by gradients. Changes in light, temperature, and water chemistry create invisible layers, like floors in a building made of physics instead of concrete. Animals learn to navigate these layers instinctively, positioning themselves where conditions suit them best. To us, it all looks the same. To them, it is a carefully arranged map written in pressure and photons. Because there is no bottom to anchor to, movement here is constant. Water masses slide past each other. Currents flow slowly but persistently, carrying organisms across vast distances. A creature born in one part of the ocean might spend its life drifting through entirely different regions without ever realizing it crossed an invisible border. National boundaries mean nothing here. The midwater is the ultimate global commons. This lack of structure also means that encounters are unpredictable. In the midwater, you do not stumble upon things the way you do on land. You intersect with them. Two drifting paths cross, and suddenly there is a predator, prey, or potential mate directly in front of you. Timing and chance play a massive role. Being in the right place at the right moment can matter more than speed or strength. From a human perspective, the midwater feels unsettling precisely because it denies us reference points. Our brains like edges. We like walls, horizons, and floors. The midwater offers none of these. It is a space that refuses to be framed, which makes it difficult to film, difficult to map, and difficult to emotionally grasp. It is an environment that does not care if you are watching. And yet, this featureless openness is what makes the midwater so important. It acts as the connective tissue of the ocean, linking surface processes with deeper systems through constant movement and exchange. It is not a void. It is a living, breathing layer of the planet, quietly circulating life and matter on a global scale. So when we talk about the midwater, we are not talking about a place you visit. We are talking about a condition, a state of existence defined by floating, drifting, and adapting to a world with no fixed points. It is the ocean's great in-between, where life has learned to survive without walls, without landmarks, and without ever truly standing still. As we drift deeper into the midwater, the most important resource quietly disappears. Not food, not space, light. Down here, light is no longer a given. It does not flood the environment or bounce generously off surfaces. Instead, it arrives weak, filtered, and exhausted, like it already used most of its energy just getting this far. For life in the midwater, darkness is not a dramatic event. It is the default setting. This permanent twilight creates a world where traditional vision becomes unreliable. Shapes blur into backgrounds. Distances become guesswork. Movement is often sensed before it is seen. For animals living here, relying solely on eyesight would be like trying to read fine print during a power outage. Possible maybe, but not a great long-term strategy. So evolution had to get creative. One solution was to change how light is used altogether. If the environment refuses to provide enough illumination, why not bring your own? In the midwater, many organisms have turned light into a tool rather than a background feature. Light becomes something you deploy intentionally, not something you passively receive. It is no longer about seeing the world clearly. It is about controlling what others see of you. This shift changes the rules of interaction. In the midwater, being visible at the wrong time can be fatal. A silhouette against faint light above is an open invitation to be eaten. At the same time, being completely invisible makes it difficult to find food or communicate. The challenge is balance. You want to exist without announcing yourself. You want to observe without being observed. It is a delicate dance, performed in near darkness. As a result, many midwater creatures have evolved eyes that are less about detail and more about sensitivity. Instead of sharp images, they prioritize detecting faint glimmers and subtle contrasts. These eyes are tuned to notice the slightest hint of light, even if it comes from far away or lasts only a fraction of a second. In this world, spotting a brief glow can be more important than recognizing a face. But vision is only part of the story. In low light, other senses step into the spotlight. Touch, vibration detection, and chemical cues become essential ways to understand the environment. Water carries information in ways air cannot. Tiny disturbances travel outward, chemical traces linger, and pressure changes ripple through the darkness. For midwater animals, the ocean is constantly whispering. They just know how to listen. Still, darkness has a psychological weight to it, even if you have never known anything else. The absence of light removes certainty. It erases clear boundaries and turns every interaction into a question mark. Is that shape food, danger, or nothing at all? In the midwater, hesitation can be costly, but recklessness is worse. Decisions must be made quickly, often with incomplete information. Evolution favors those who guess correctly more often than not. This environment also changes how time feels. Without strong light cycles, days blur together. The rhythm of life becomes detached from sunrise and sunset, replaced by subtler cues that signal when to move, when to feed, and when to stay still. It is a slower, more deliberate existence, paced by energy conservation rather than urgency. Every movement has a cost, and in the dark, wasted effort is especially unforgiving. Darkness also acts as a great equalizer. Size, speed, and aggression matter less when visibility is limited. A small, careful organism can thrive alongside larger ones by simply being harder to detect. In many cases, the most successful strategy is to look like nothing at all. Not threatening, not interesting, just another patch of darkness drifting by. And yet, despite the challenges, this twilight world is not bleak. It is full of subtle beauty. Faint glows appear and vanish. Shadows slide past each other in slow motion. Encounters happen quietly, often without spectacle. It is a realm that rewards patience and awareness rather than brute force. Living without light forces life to redefine what awareness means. It is no longer about seeing everything clearly. It is about sensing just enough to survive. The Midwater teaches its inhabitants that vision is optional, but perception is not. And as we move forward, we will see how this darkness did not limit life, but instead pushed it towards some of the most ingenious solutions the ocean has ever produced. If darkness is the rule in the Midwater, then bioluminescence is the loophole. This is not borrowed light or reflected glow. This is light made from scratch, generated inside living bodies through chemistry that turns energy into illumination. It is one of the most widespread and versatile tools in the Midwater, and once you start noticing it, you realize this supposedly dark realm is constantly flickering with tiny, deliberate sparks. At its core, Bioluminescence is a chemical reaction. Special molecules inside an organism react with oxygen, releasing energy in the form of light instead of heat. No sparks, no flames, just cold, efficient glow. It is the kind of lighting that would make engineers jealous, because nearly all the energy goes into producing light rather than wasting it. Nature, once again, solved a problem we are still arguing about in meetings. What makes bioluminescence truly fascinating is not just how it works, but how precisely it is controlled. This is not accidental glowing. Animals can turn it on and off, adjust its intensity, and in some cases even shape it into patterns. Light becomes a language, a weapon, a disguise, and sometimes a dating profile, all rolled into one glowing package. For predators, light can be a lure. In a place where food is scattered and encounters are rare, attracting prey is far more efficient than chasing it. A small, harmless-looking glow drifting in the darkness can be irresistible to curious animals. They approach, investigate, and suddenly realize they have made a career-ending mistake. The glow was never the point. The mouth attached to it was. Bioluminescence can also be used defensively. When threatened, some animals release clouds of glowing material into the water, creating a sudden burst of light that disorients predators. Imagine trying to chase dinner and someone throws a flashbang grenade made of plankton. The predator is left confused, blinking metaphorically, while the glowing animal slips away into the darkness it knows so well. Then there is camouflage, which sounds counterintuitive until you think about it. In the midwater, faint light from above can outline an animal's silhouette, making it visible from below. Some creatures solve this by producing light on their undersides, carefully matching the brightness of the dim glow above them. The result is visual erasure. From below, the animal blends seamlessly into the background, like a floating cutout that forgot to exist. It is invisibility, achieved not by darkness, but by imitation. Communication is another major use of bioluminescence. In a world where sound travels well, but vision does not, a brief flash of light can carry a lot of meaning. Different species use distinct patterns, rhythms, and colours to signal to one another. Some flashes say, "This is my territory." Others say, "Do not eat me." And some, inevitably, say, "Hello, I am single and surprisingly luminous." Reproduction in the midwater can be particularly challenging. Finding a partner in an open, dark environment is like trying to meet someone in a city where there are no streets, no addresses, and everyone is drifting. Bioluminescence helps narrow the search. Species-specific light patterns ensure that signals reach the right audience, preventing awkward misunderstandings that could waste precious energy or attract the wrong kind of attention. Not all glowing comes from the animals themselves. Some species outsource their lighting needs by hosting bioluminescent bacteria. These tiny partners live inside specialized organs, producing light continuously, while the host controls when and how it is revealed. It is a symbiotic arrangement that benefits both sides. The bacteria get a safe place to live, and the host gets a built-in flashlight that never needs new batteries. Color also matters. In the midwater, blue light travels farthest, which is why most bioluminescence appears blue or blue-green. Red light, on the other hand, fades quickly in water, making it nearly invisible unless you are very close. Some animals exploit this by producing red light that only they can see, creating a private spotlight system that lets them illuminate prey without alerting it. It is the underwater equivalent of night vision goggles, except grown organically. Bioluminescence turns darkness into opportunity. It allows animals to rewrite the rules of visibility, choosing when to be seen and when to vanish. It transforms the midwater from a place defined by absence into one shaped by intentional signals and fleeting glimmers. The ocean may be dark, but it is never truly unlit. It is alive with purposefully placed sparks, each one telling a story, sending a message, or setting a trap. In the midwater, light is not just something you see, it is something you use. If there is a mascot for the midwater, it might just be the lanternfish. Not because they are the biggest, scariest, or flashiest, but because they are everywhere, quietly, persistently, in numbers so vast they reshape the ocean simply by existing. At first glance, lanternfish seem unremarkable. They are small, usually no longer than a human finger, with simple fish shapes and modest personalities. And then they turn on the lights. Lanternfish are named for rows of tiny light-producing organs embedded along their bodies. These organs are arranged in precise patterns, unique to each species, like glowing fingerprints. When viewed from a distance in the dark midwater, these patterns resemble constellations drifting through space. It is as if the night sky fell into the ocean and learned how to swim. These glowing arrangements are not decorative accidents. They are highly specific, carefully positioned, and remarkably consistent. Scientists can identify different lanternfish species simply by the placement of their lights, much like birdwatchers recognize species by wing patterns. In a world where color is unreliable and shapes blur, light patterns become identity. Lanternfish use these lights primarily for recognition and coordination. When you are a small fish in a massive, open environment, finding others like you is essential. Glowing patterns allow lanternfish to locate members of their own species without drawing unnecessary attention from outsiders. It is a delicate balance between being visible enough to communicate and subtle enough to survive. But lanternfish are not just social glow sticks drifting aimlessly. They are active participants in the midwater ecosystem. Their small size hides an outsized impact. Collectively, lanternfish are among the most abundant vertebrates on Earth. There are so many of them that their combined weight may exceed that of all humans, livestock, and wild land animals put together. That is a lot of tiny teeth, making a very big difference. Their feeding habits help regulate populations of smaller drifting organisms, keeping the midwater from tipping into chaos. By consuming vast quantities of planktonic prey, lanternfish act as living filters, shaping the flow of energy through the ocean. They may be small, but they are busy, and the ocean notices when they are around. Lanternfish also have bodies perfectly suited to their environment. They are streamlined but not built for speed. Instead, they favor efficiency. Their muscles are designed for steady movement rather than bursts of power, conserving energy in a place where calories are precious. Every flick of the tail is calculated, not flashy. Their eyes are large relative to their heads, optimized to detect faint glows and subtle contrasts in the dark. They are not scanning for fine detail, but for presence. A flash, a shadow, a hint that something is there when nothing should be. In the midwater, awareness beats clarity every time. Despite their gentle appearance, lanternfish are not defenseless. Their small size makes them less attractive targets for some predators, and their glowing patterns can confuse attackers, breaking up their outline and making it harder to judge distance or speed. In a dark environment, misjudging your prey by even a few centimeters can mean missing your chance entirely. What truly sets lanternfish apart, though, is how they link different parts of the ocean together. Their daily movements, rising and sinking through the water column, transport nutrients and energy across vast vertical distances. They are not just residents of the Midwater, they are couriers, quietly shuttling resources through the ocean like glowing delivery trucks on a nightly route. This makes lanternfish a cornerstone species. Remove them, and the entire system would wobble. Predators would lose a major food source. Prey populations would surge unchecked. The balance of the Midwater would shift in unpredictable ways. All because a handful of small, glowing fish stopped doing what they have done for millions of years. There is something poetic about lanternfish. In a place defined by darkness and emptiness, they create patterns of light that mirror the stars above. They turn the Midwater into a living sky, one where constellations move, interact, and occasionally get eaten. They remind us that importance is not always loud or obvious. Sometimes it glows softly, in steady rows, drifting through the dark and holding an entire ecosystem together without ever asking for attention. Every evening, as the sun slips below the horizon and the ocean surface darkens, something extraordinary begins. It does not make headlines, it does not leave footprints, but in terms of scale, it dwarfs every land migration combined. Billions of animals, from tiny drifting organisms to small fish, begin moving upward through the water column in a slow, coordinated ascent. No one blows a whistle. No one gives instructions. The ocean simply knows it is time. This phenomenon is called vertical migration, and it happens every single day. As night falls, life rises. As dawn approaches, it sinks again. This rhythmic movement turns the ocean into a living elevator system, carrying biomass up and down over hundreds of meters with clock-like precision. If you could see it from the side, the ocean would look like it was breathing. The motivation behind this daily commute is simple but powerful. Near the surface, food is more plentiful. Microscopic plants grow there, feeding the base of the food web. But the surface is also dangerous. Light reveals silhouettes. Predators patrol. Being visible during the day is an invitation to trouble. So midwater animals have struck a compromise. They visit the surface under the cover of darkness, feed quickly, and retreat to safer depths before the sun returns. This behavior is not limited to one type of organism. It involves an entire cast of characters moving in loose synchrony. Tiny drifting animals rise alongside small fish, gelatinous creatures, and other midwater residents. Each group moves at its own pace, but the overall direction is the same. Up at night, down by day. It is a massive, layered flow of life, happening invisibly beneath ships and shorelines. What makes vertical migration remarkable is its consistency. These animals do not need to see the sun to know when to move. They respond to subtle changes in light intensity, sensing when darkness deepens enough to signal safety. Even on cloudy nights or in rough seas, the timing remains precise. The ocean runs on internal clocks, and vertical migration is one of its most reliable routines. The energy cost of this movement is significant. Swimming hundreds of meters up and down every day is not easy, especially for small animals with limited reserves. That means the benefits must outweigh the risks. Feeding near the surface provides access to richer food sources, allowing animals to refuel efficiently. By returning to deeper water during daylight, they reduce the chance of being eaten. It is a daily gamble that usually pays off. Vertical migration does more than help individual animals survive. It plays a major role in how the ocean functions as a whole, as migrating organisms feed near the surface and then descend. They transport organic material downward. Waste products, shed material, and eventually bodies carry nutrients into deeper layers of the ocean. This process helps regulate carbon and nutrient cycles on a global scale. In other words, this daily commute helps keep the planet running. From a physical perspective, this mass movement even affects how sound travels in the ocean. Dense layers of migrating animals can reflect sonar signals, creating what early scientists once mistook for the seafloor. The ocean, it turns out, has a habit of pretending to be something it is not, especially when billions of tiny commuters are involved. For predators, vertical migration shapes hunting strategies. Some species position themselves along the migration routes, intercepting animals as they move. Others time their activity to match the ascent or descent, taking advantage of moments when prey is concentrated and predictable. The daily rise and fall of life creates patterns that ripple through the entire food web. What is especially fascinating is how flexible this behavior can be. In regions where surface conditions change, migration depths and timing adjust accordingly. Animals fine-tune their movements based on local light levels and risk. It is not a rigid schedule, but a responsive one, constantly recalibrated by the environment. Despite its importance, vertical migration remained poorly understood for a long time. It is hard to observe directly, happens mostly at night, and involves creatures that are difficult to track. Only with modern instruments did scientists realize just how immense and coordinated this movement truly is. The ocean had been hosting the largest migration on Earth all along, and we barely noticed. Vertical migration reminds us that the ocean is not static. It is dynamic, rhythmic, and alive with motion. While we sleep, the sea shifts its weight, lifting and lowering life on a planetary scale. It is a daily reminder that even in the dark, even far from shore, the ocean is constantly on the move, following patterns older than humanity and far larger than anything we build on land. At first glance, jellyfish and siphonophores do not look like predators. They look like accidents. Like someone dropped a clear umbrella into the ocean and it just kept floating out of politeness. Their bodies are soft, see-through, and often barely visible at all. If you judge them by appearance alone, you would assume they spend their lives doing nothing in particular. This is a dangerous assumption. These drifting organisms are masters of passive predation. Instead of chasing prey, they let the ocean do the work. Their bodies are built to interact with moving water, stretching delicate tentacles outward like invisible tripwires. When something bumps into them, the encounter is usually brief and decisive. The prey never sees it coming, which is impressive considering the predator barely looks like it exists. Jellyfish are not fish at all, but simple animals built around a basic body plan that has survived for hundreds of millions of years. They have no brains, no bones, and no centralized control system. Instead, they operate through nerve nets that coordinate movement and feeding without conscious thought. It is less like making decisions and more like executing a well-tested algorithm that has never needed an update. Siphonophores take this simplicity and turn it into something even stranger. A siphonophore is not a single animal, but a colony of specialized units working together as one. Each unit has a job. Some handle movement, others capture food, others focus on reproduction. Individually, they cannot survive. Together, they function as a single, elongated predator drifting through the midwater like a living assembly line. Despite their fragility, these organisms are remarkably effective hunters. Their tentacles are armed with specialized stinging cells that fire faster than human reflexes. Once triggered, they inject toxins that immobilize prey almost instantly. The process is so fast and efficient that the prey often does not realize what happened until it is already being transported toward the mouth. It is ambush predation, perfected through patience rather than speed. Their transparency is not a coincidence. By allowing light to pass straight through their bodies, jellyfish and siphonophores minimize their visual footprint. In the dim midwater, this makes them extremely difficult to detect. There is no outline, no strong contrast, just a vague distortion in the water that most animals will never notice until it is too late. Being invisible is often better than being fast. Movement for these drifters is subtle. Jellyfish pulse gently, contracting and relaxing their bells to propel themselves forward. It is not efficient in terms of speed, but it is efficient in terms of energy. Siphonophores rely even more heavily on currents, adjusting their orientation and structure to stay in favorable flows. They go where the food goes, without wasting effort trying to outswim it. What makes these predators particularly suited to the midwater is their adaptability to scarcity. They do not need frequent meals. Their low-energy lifestyles allow them to survive long stretches between successful captures. When prey does arrive, they are ready. Tentacles extended, stinging cells primed. The system waits patiently, like a trap that never needs resetting. Jellyfish and siphonophores also play an important role in controlling populations of smaller drifting organisms. By feeding on abundant prey, they help prevent any one group from overwhelming the system. This balance is not deliberate, but it is effective. The midwater relies on such quiet regulators to maintain stability in an environment where resources are unevenly distributed. There is also an elegance to how these creatures exist. Without rigid structures, their bodies flow with the water rather than resisting it. Pressure changes do not bother them. Damage can often be repaired or tolerated. In a place where being stiff can be a disadvantage, softness becomes strength. Their presence challenges our assumptions about what it means to be a predator. No jaws snapping, no dramatic chases, just patience, chemistry, and a deep understanding of physics. Jellyfish and siphonophores remind us that in the midwater, dominance does not always look intimidating. Sometimes it looks like a floating, transparent shape drifting calmly through the dark, quietly waiting for the ocean to deliver dinner directly into its arms. Some creatures in the midwater survive by glowing. Others survive by vanishing. The hatchetfish, however, survives by committing fully to being visually confusing. At first glance, it looks like someone took a normal fish and squashed it sideways with great enthusiasm. Its body is tall and thin, shaped like the blade of a hatchet, with a narrow edge facing forward. It is not a design you would expect to work. And yet, in the midwater, it works beautifully. The hatchetfish's strange shape is not an aesthetic choice. It is an optical strategy. In the dim light of the midwater, predators often look upward, searching for silhouettes against faint light from above. A wide-bodied fish would cast a noticeable shadow, The hatchetfish solves this by presenting the smallest possible profile when viewed from below. Seen head-on, it is almost invisible, like a thin line drifting in the water. This vertical flattening dramatically reduces how much of the fish can be seen from critical angles. Instead of advertising its presence, the hatchetfish minimizes it. In a world where being noticed is often a death sentence, subtle geometry can be life-saving. Evolution, it turns out, is very good at spatial reasoning. Then there is the shine. Hatchetfish are covered in silvery, reflective scales that act like tiny mirrors. These scales do not simply sparkle randomly. They reflect the surrounding light, blending the fish into the background by matching whatever faint glow exists around it. From the side, the fish becomes a moving reflection of the water itself. It does not look like an object. It looks like absence. This mirror-like camouflage works best in the midwater's soft, diffuse lighting. There are no strong beams or sharp contrasts, just a general glow that shifts with depth and time of day. By reflecting this ambient light, the hatchetfish avoids standing out. It is the aquatic equivalent of wearing a perfectly matched camouflage outfit in an environment where fashion mistakes are fatal. The fish's eyes add another layer to this strategy. Positioned to look upward, they are tuned to detect shapes and movement against the dim background above. This allows the hatchetfish to monitor potential threats and opportunities without drawing attention to itself. It watches, but it does not announce that it is watching. Despite its unusual body plan, the hatchetfish is an active predator. It feeds on smaller drifting organisms, using quick bursts of motion to capture prey. These movements are short and precise, conserving energy and minimizing disturbance. There is no dramatic chase, just a sudden adjustment and a quick snap. Efficiency is the name of the game. The hatchetfish's lifestyle reflects the broader logic of the midwater. With no physical cover to hide behind, the body itself becomes the hiding place. Shape, orientation, and reflectivity all work together to create a moving illusion. The fish is not trying to be invisible in absolute terms. It is trying to be uninteresting, blending into the visual noise of the environment. This strategy also highlights an important aspect of midwater survival. Evolution here is not about looking intimidating or impressive. It is about solving very specific visual problems. How do you exist in open water without casting a shadow? How do you move without creating a recognizable outline? The hatchetfish answers these questions with geometry and optics rather than brute force. There is something quietly clever about this approach. While other animals invest energy into producing light or complex behaviors, the hatchetfish lets physics do most of the work. Its body is a tool that interacts with light in predictable ways. It is a living demonstration of how form and function merge in environments where visibility is the primary battlefield. In the end, the hatchetfish reminds us that survival does not always favor the fastest, the strongest, or the most aggressive. Sometimes, it favors the animal that looks like a floating sliver of nothing, polished to a shine, drifting through the midwater like a misplaced reflection. In the dark ocean, being shaped like a flying axe and shiny as a spoon is not strange at all. It is smart. Camouflage usually brings to mind stripes, spots, and patterns that help animals blend into forests, deserts, or coral reefs. But the midwater offers none of that. There are no backgrounds to match, no textures to imitate, and no places to hide. In this open, three-dimensional space, camouflage has to work differently. Here, survival depends on becoming visually irrelevant. One of the most effective strategies in open water is transparency. Many midwater creatures are almost completely see-through, allowing light to pass through their bodies with minimal distortion. Instead of reflecting or absorbing light, they let it go right through, leaving little for the eye to detect. Organs are reduced, rearranged, or tucked away to minimize visibility. It is not perfect invisibility, but it is close enough to fool most predators most of the time. Transparency works best when combined with stillness. Movement creates ripples, shifts, and outlines that give away even the clearest body. That is why many transparent organisms drift rather than swim actively. They move with the water, matching its speed and direction. When everything is moving together, it becomes harder to pick out an individual. The ocean itself becomes the disguise. Another powerful technique is counter-illumination, which tackles one of the biggest problems in the midwater: shadows. Even faint light from above can cast a silhouette, revealing an animal's shape to predators below. Counter-illumination solves this by producing light on the underside of the body, carefully calibrated to match the brightness of the light filtering down from above. When done correctly, the animal's shadow disappears. This is not random glowing. It requires precise control. Too much light, and the animal becomes a beacon. Too little, and the silhouette remains visible. Many midwater animals can adjust the intensity of their underside glow in real time, responding to changes in light conditions. It is a dynamic form of camouflage, constantly fine-tuned as the environment shifts. Some species take camouflage even further by manipulating surface textures. Instead of smooth outlines, they have irregular edges, frills, or elongated appendages that break up their shape. In low light, this makes it harder for predators to recognize a familiar form. The brain struggles to categorize what it cannot easily define. Confusion, in this case, is protection. Color plays a role too, but not in the way we might expect. Bright colors are rare in the midwater because they serve little purpose in low light. Instead, many animals are dark, absorbing what little light exists to avoid reflection. Others are silvery, reflecting the surrounding environment, rather than displaying their own coloration. Both strategies aim for the same outcome: not standing out. Orientation is another subtle but important factor. Some animals adjust how they position their bodies relative to incoming light, presenting minimal surface area to potential observers. By angling themselves just right, they reduce the chance of being detected. It is camouflage through posture, a quiet adjustment that can mean the difference between safety and danger. Camouflage in the midwater is not limited to prey. Predators use it as well. Remaining unseen allows them to approach prey more closely, increasing the odds of a successful capture. In an environment where encounters are rare, getting one good chance matters. Being invisible until the last moment is often the most effective hunting strategy. What makes all of this remarkable is how precise it has become. These are not crude approximations. They are finely tuned solutions honed over millions of years. The midwater does not forgive sloppy designs. Even small mismatches in light, movement, or shape can be detected by eyes trained to notice the slightest anomaly. Camouflage here is less about hiding and more about erasing. Erasing outlines, erasing shadows, erasing signals that say there is something here. It is an art form built on understanding how light behaves in water and how vision works under extreme conditions. In the end, open water camouflage shows us that invisibility is not a single trick, but a toolkit. Transparency, Counter-illumination, reflectivity, posture, and motion all work together to reduce detectability. The midwater is not a place where you blend in with scenery. It is a place where you blend in with nothing at all. Few animals in the ocean suffer from a worse public image than the vampire squid. The name alone suggests a nightmarish creature lurking in the darkness, fangs bared, thirsting for blood. In reality, the vampire squid is about as threatening as a soggy umbrella with feelings. It neither sucks blood nor behaves like a squid in the traditional sense. It is, instead, a master of survival in one of the most challenging environments on Earth, misunderstood largely because it looks dramatic and lives in the dark. The vampire squid occupies a very specific niche in the midwater, one where oxygen levels are extremely low. Most animals avoid these zones because breathing becomes difficult and energy demands increase. The vampire squid does the opposite. It thrives there. Its body is built to function efficiently when oxygen is scarce, allowing it to live where fewer competitors and predators can tolerate the conditions. It chose the quietest corner of the ocean and made it home. Physically, the vampire squid is a small, soft-bodied animal with large eyes and webbing that connects its arms, giving it a cape-like appearance when spread out. This feature is partly responsible for its spooky reputation. When threatened, it can curl its arms over its body, exposing spiky-looking projections. It looks intimidating, but this is mostly for show. The spikes are not weapons, just modified structures that make the animal appear larger and less appealing to predators. Unlike true squids and octopuses, the vampire squid has a unique feeding strategy. It does not chase prey or grapple with struggling animals. Instead, it feeds on marine snow, a slow rain of organic particles drifting down through the water. This material includes bits of dead organisms, waste, and other debris. It is not glamorous food, but it is reliable. The vampire squid collects this material using long, sticky filaments, drawing it in like a very patient vacuum cleaner. This diet makes the vampire squid an energy minimalist. It does not need to move quickly or frequently. Its metabolism is exceptionally low, allowing it to survive on sparse resources in an environment where food is unpredictable. While other animals burn, energy searching and chasing, the vampire squid waits. In the midwater, patience can be more valuable than speed. Defense is another area where the vampire squid breaks expectations. Instead of ink clouds like other cephalopods, it releases a cloud of bioluminescent mucus when threatened. This glowing substance distracts and confuses predators, creating a luminous decoy while the vampire squid drifts away. It is less dramatic escape and more polite disappearance, but it works. Its large eyes are adapted to detect extremely low light levels, helping it navigate its dim environment without drawing attention to itself. These eyes are not about sharp vision, but about sensitivity. They are tuned to notice faint changes rather than detailed images, perfectly suited to a life spent in perpetual darkness. The vampire squid's body is also unusually delicate. It lacks the strong muscles seen in more active cephalopods, reinforcing its slow, drifting lifestyle. This softness is not a weakness. It allows the animal to tolerate pressure changes and conserve energy. In a harsh environment, being gentle with your own biology can be an advantage. What makes the vampire squid truly fascinating is how completely it has rejected the typical predator narrative. It does not hunt aggressively. It does not fight. It does not dominate. Instead, it survives by occupying a space others avoid, eating what others ignore, and reacting only when absolutely necessary. It is the ocean's ultimate introvert. The name vampire squid is a reminder of how human imagination often misfires when confronted with unfamiliar life. We see darkness and assume danger. We see strange shapes and invent menace. The reality is far more nuanced. This animal is not a monster. It is a specialist, finely tuned to a narrow slice of the ocean that most creatures cannot tolerate. In the end, the vampire squid teaches us that survival does not require ferocity. Sometimes, it requires finding a quiet place, lowering your energy demands, and making the most of what slowly drifts your way. Not exactly a horror story, but an impressive evolutionary success, unfortunate branding aside. As you descend through the ocean, pressure becomes an unavoidable fact of existence. Water is heavy, and it stacks relentlessly. Every meter adds more weight, pressing inward from all sides. By the time you reach the midwater, the pressure is already many times greater than at the surface. It does not crush dramatically like in the movies. It simply never stops pressing. For animals living here, this constant squeeze shapes every aspect of their biology. Pressure affects anything that contains air or rigid spaces. At depth, gases compress, cavities shrink, and anything brittle risks breaking. That is why midwater animals tend to be soft, squishy even. Flexibility is not just convenient here, it is essential. A body that can deform without breaking handles pressure far better than one built around stiff, fragile structures. Many midwater animals lack rigid skeletons altogether. Instead of hard bones, they rely on soft tissues and cartilage-like materials that compress smoothly. This allows their bodies to withstand changes in pressure as they move up and down through the water column. A crunchy body might hold its shape nicely at the surface, but at depth, it would be under constant stress, like a soda can waiting to be crushed. Fluids play a major role in this strategy. Water is largely incompressible, meaning it resists changes in volume under pressure. By filling their bodies with fluids rather than gases, midwater animals avoid the problems associated with compression. Their internal environment remains stable even as external pressure increases. In essence, they become pressure neutral, blending into the surrounding water rather than fighting it. This has important implications for buoyancy as well. Without air-filled spaces like lungs or swim bladders, many midwater animals achieve neutral buoyancy through tissue composition rather than trapped gas. They hover effortlessly, expending little energy to stay at a particular depth. Floating becomes a passive state, not an active struggle. Pressure also influences how muscles work. At depth, muscle tissue behaves differently, and high-speed movement becomes energetically expensive. This encourages lifestyles built around slow, deliberate motion. Midwater animals are rarely sprinters. They are gliders, drifters, and ambushers. Quick bursts are possible, but only when absolutely necessary. Cells themselves must adapt to pressure. Proteins and membranes can change shape under extreme conditions, potentially disrupting basic biological processes. Midwater organisms have molecular adaptations that keep these structures functioning properly, despite the squeeze. It is chemistry under pressure, literally, and it allows life to operate normally in environments that would break unprepared cells. Even sensory systems are shaped by pressure. Structures that rely on air or rigid frameworks are less common. Instead, senses are often based on fluid movement and chemical detection. which perform reliably under compression. The ocean does not forgive designs borrowed from land. Everything must work, while being pressed from all sides. The result of all this is a community of animals that look soft and delicate, but are actually well suited to their environment. Their squishiness is strength. It allows them to survive pressure changes, conserve energy, and avoid catastrophic failure. A rigid body might seem sturdy, but in the midwater, it would be under constant threat from forces it cannot escape. This softness also contributes to the ghostly appearance of many midwater species. Without hard edges or dense structures, bodies appear translucent or amorphous. Shapes blur into the background, adding another layer of subtle camouflage. Pressure adaptation and visual concealment often go hand in hand. From a human perspective, squishy animals may seem fragile. We associate firmness with durability. The midwater flips that assumption completely. Here, resilience comes from yielding, not resisting. Being able to bend, compress, and flow with the environment is far safer than standing stiffly against it. Pressure is an invisible sculptor, quietly shaping life in the midwater. It rewards designs that embrace flexibility and punishes those that cling to rigidity. In this world, being crunchy is a liability. Being soft is survival. Finding food in the midwater is not a matter of walking to the nearest restaurant. Meals are scattered, unpredictable, and often separated by long stretches of nothing at all. There is no reef to graze, no seafloor to rummage through, no plants growing nearby. Food appears when it appears, and when it does, you have to be ready. This reality has pushed midwater animals toward feeding strategies that look extreme, inefficient, or downright absurd, but make perfect sense in context. One of the most striking solutions is simply having an enormous mouth. In the midwater, prey items can be few and far between, so the ability to eat whatever happens to drift close is a major advantage. Some animals have jaws that can open incredibly wide, allowing them to engulf prey nearly as large as themselves. It is not about being picky. It is about opportunity. If it fits, it counts. These oversized mouths are often paired with expandable stomachs and flexible jaws. Instead of rigid limits, these animals operate on the principle of maximum intake. A large meal might need to last a long time, so missing it is not an option. When food finally shows up, the strategy is simple. Do not let it escape just because it is inconveniently large. Other midwater predators take the opposite approach. Rather than expanding to accommodate any prey, they slow everything down. Slow-motion ambush predators rely on patience rather than pursuit. They drift nearly motionless, conserving energy, waiting for prey to wander within striking distance. When they do move, it is quick and precise, minimizing effort and maximizing success. This strategy works because movement in the midwater is often subtle and uncoordinated. Many potential prey items are themselves drifting, carried by currents rather than actively swimming. By positioning themselves correctly, ambush predators let the environment deliver food directly to them. It is hunting by waiting, an approach that fits perfectly in an ecosystem where energy conservation is critical. Some animals combine both strategies, pairing a large mouth with a low-energy lifestyle. They do not chase prey, but they are prepared to eat whatever arrives. This combination reduces the need for frequent meals and allows survival during long periods of scarcity. In the midwater, versatility is often more valuable than specialization. Feeding strategies here also reflect the risk of attracting attention. Chasing prey creates movement and disturbance, which can draw in larger predators. By limiting activity, midwater hunters reduce their own visibility. Eating becomes a quiet affair, often over in seconds, followed by long periods of stillness. It is not dramatic, but it is effective. Some midwater animals feed on extremely small prey, collecting it in large quantities rather than targeting individuals. This requires specialized structures to capture and process tiny food items efficiently. Instead of a single dramatic meal, they rely on steady intake over time. This approach works well when small prey is abundant, but larger targets are rare. The diversity of feeding strategies highlights how flexible life has become in this environment. There is no single correct way to eat in the midwater. Success depends on matching your strategy to your body, your energy budget, and the type of food you can reliably access. Evolution has tested countless approaches, and the ones that remain are those that strike the right balance between effort and reward. What unites all these strategies is an understanding of scarcity. Midwater animals are not wasteful. They do not assume another meal is just around the corner. Every capture matters. Every bite counts. Whether through oversized mouths, slow ambushes, or efficient collection of small prey, these animals are built to make the most of rare opportunities. From the outside, these feeding methods can look bizarre or excessive. Why have a mouth that large? Why wait so long between meals? But in the midwater, these are not excesses. They are adaptations to a world where food does not come with guarantees. When meals are rare, you either wait patiently, or you make sure that when food finally appears, you are physically incapable of saying no. In the dim world of the midwater, light is scarce, but information is hidden inside what little exists. To find it, some animals have taken the concept of vision and turned the volume all the way up. The result is eyes so large they dominate the head, giving these creatures an expression that looks permanently shocked by the state of the universe. Among the most famous examples is the barreleye fish, a quiet observer built almost entirely around the act of seeing. The barreleye's most striking feature is its pair of tubular eyes, housed inside a transparent, fluid-filled dome. These eyes are oriented upward, like periscopes, constantly scanning the faint glow filtering down from above. This arrangement allows the fish to detect small, subtle shapes passing overhead, even when light levels are incredibly low. In the midwater, looking up is often more useful than looking forward. Large eyes are not just about size for size's sake. Bigger eyes gather more light, increasing sensitivity in dark environments. Think of them as biological light buckets, collecting every possible photon and directing it toward the retina. This makes it possible to detect faint glimmers that smaller eyes would completely miss. In a place where light is rare, missing information can mean missing food or danger. The structure of these eyes is just as important as their size. Barreleye eyes are tubular, meaning they focus light more precisely from a narrow field of view. This sacrifices peripheral vision in favor of enhanced sensitivity and clarity in a specific direction. It is a trade-off that makes sense when the most important information comes from above, where silhouettes and faint bioluminescent flashes appear. The transparent dome that covers the barreleye's eyes adds another layer of adaptation. It protects the eyes while allowing light to pass through with minimal distortion. It also allows the fish to rotate its eyes within the dome, changing its field of view without moving its body. This is a clever way to observe the environment while remaining as still and inconspicuous as possible. Large eyes do come with costs. They take up space and require energy to maintain. In the midwater, where resources are limited, this means vision must provide significant benefits to justify the investment. For animals like the barreleye, those benefits are clear. Detecting prey silhouetted against faint light gives them access to food that others might overlook. The exaggerated eye size also influences behavior. Animals with giant eyes often rely on careful observation rather than active pursuit. They watch, track, and wait for the right moment. Movement is minimal. Attention is constant. It is a strategy built around information gathering rather than force. Interestingly, not all midwater animals choose this path. Some reduce or even lose their eyes entirely, relying on other senses. The fact that both approaches exist highlights how varied survival strategies can be in the same environment. Giant eyes represent one solution among many, but for species that use them, they are central to how they experience the world. From a human perspective, these eyes can look comical or unsettling. We are used to associating large eyes with youth or surprise, not with quiet, drifting fish. But in the midwater, expression is irrelevant. Function is everything. Those oversized eyes are not for charm. They are tools, honed to extract meaning from darkness. The barreleye fish, in particular, feels almost contemplative. Drifting slowly, eyes fixed upward, it seems to be perpetually watching something just out of view. In reality, it is reading the faintest cues in a low-light environment, responding to information we would never notice. It is not startled. It is focused. Giant eyes remind us that perception shapes reality. In the midwater, where light is limited and fleeting, the ability to see even a little better can open up entirely new opportunities. For these animals, looking permanently surprised is not a side effect. It is the face of success in a world where every photon counts. When light becomes unreliable, the ocean does not fall silent. In fact, it becomes louder in ways that matter deeply to the creatures living in the midwater. Sound travels exceptionally well through water, moving faster and farther than it does in air. In the darkness, vibrations carry information long before anything becomes visible. For many midwater animals, the ocean is less like a place you see and more like a place you listen to. Every movement creates vibrations. A flick of a tail, the pulse of a drifting body, even the subtle flow of water around an object sends ripples outward. These ripples do not vanish immediately. They spread, overlap, and reflect, filling the water with a constant background hum. To us, this might seem like noise. To midwater animals, it is a detailed map of nearby activity. Many fish and invertebrates are equipped with sensory systems that detect changes in water movement with remarkable precision. These systems do not rely on ears in the way humans think of them. Instead, they use specialized cells and structures that respond to pressure changes and vibrations. This allows them to sense approaching predators, nearby prey, and even the movement of distant animals long before visual confirmation is possible. In a dark environment, this early warning system is invaluable. Detecting something before it is close enough to see gives animals time to react. They can freeze, drift away, or prepare to strike. Sound and vibration provide context when vision cannot, filling in the gaps left by low light. The ocean's acoustics also allow animals to communicate over distances that would be impossible visually. Low-frequency sounds can travel for kilometers, passing through layers of water with minimal loss of energy. Some midwater animals produce sounds intentionally, using them to signal presence, establish spacing, or coordinate behavior. These signals are often subtle, designed to be detected by the right audience without broadcasting to the entire ocean. Even animals that do not actively produce sound benefit from passive listening. By interpreting the rhythm and intensity of vibrations, they can distinguish between harmless background motion and something worth paying attention to. A drifting object feels different from a swimming predator. A struggling prey item sends a different signal than a calm neighbor. The water carries these clues faithfully. This reliance on sound shapes behavior in profound ways. Sudden movements are risky because they create strong, detectable vibrations. Many midwater animals move smoothly and deliberately, minimizing disturbance. Stillness is not just about visual camouflage. It is about acoustic discretion. The quieter you are, the less likely you are to be noticed. The ocean is also filled with natural sounds unrelated to animals. Water movement, distant currents, and even geological activity contribute to a complex acoustic background. Midwater animals have evolved to filter this information, tuning out irrelevant noise while remaining sensitive to meaningful signals. It is a form of constant subconscious analysis, happening without thought or effort. From a human perspective, this soundscape is difficult to imagine. We associate darkness with silence. In the midwater, darkness is paired with information-rich vibration. The ocean becomes a concert hall, where every movement adds to the performance, and every listener is also a potential instrument. As depth increases, the importance of sound often grows. Visual cues fade, but vibrations remain reliable. This shifts the balance of senses, making hearing and vibration detection central to survival. Animals that excel at interpreting these signals gain a significant advantage, navigating the darkness with confidence rather than guesswork. The midwater's acoustic environment also makes it sensitive to disruption. Unnatural sounds can travel far and persist, altering the sensory landscape. For animals that rely heavily on vibration cues, changes in background noise can affect behavior, orientation, and interaction. The ocean's concert hall has its own rules, and sudden changes to the soundtrack matter. Sound and vibration detection remind us that perception is shaped by environment. In the midwater, sight is limited, but information is everywhere if you know how to sense it. Life here does not stumble blindly through the dark. It listens, feels, and interprets a world alive with motion. In this very dark, very wet concert hall, survival depends on hearing the right notes at the right time. Predators in the midwater do not announce themselves with speed or spectacle. There is no dramatic chase, no sudden explosion of motion across a visible landscape. Instead, predation here is quiet, calculated, and deeply unsettling if you stop to think about it. The dragonfish is a perfect example. It does not look fast. It does not look bulky. What it looks like is a collection of sharp ideas that all point in the same direction. Make sure nothing escapes. The first thing you notice about a dragonfish is its mouth, or more specifically, its teeth. They are long, needle-like, and angled inward, forming a cage rather than a cutting surface. These teeth are not built for chewing. They are built for trapping. Once prey enters that mouth, backing out is not an option. It is less a bite and more a closing of doors behind you. What makes these teeth even more effective is their transparency. Instead of reflecting light and giving away the predator's position, the teeth allow light to pass through them. In the dim midwater, this means the mouth does not appear as a bright, obvious danger zone. Prey can drift closer without recognizing the threat until it is already inside it. It is a visual trick, so subtle it feels unfair. Dragonfish bodies are long and slender, built for hovering rather than sprinting. They do not waste energy chasing prey across open water. Instead, they wait, motionless, patient. In an environment where movement attracts attention, stillness becomes a hunting strategy. The dragonfish blends into the background, becoming just another dark shape among many, until the moment it decides not to be. Their heads are disproportionately large compared to their bodies, allowing room for wide-opening jaws and powerful muscles. This design prioritizes capture over endurance. A successful strike ends the interaction quickly. There is no prolonged struggle. Energy is conserved, risk is minimized, and the predator returns to waiting. Unlike surface predators that rely on speed or coordination, midwater predators like dragonfish rely on inevitability. Their design assumes that encounters will be rare, so when one happens, it must succeed. Every feature supports this philosophy. Large mouths, trapping teeth, bodies that minimize effort. It is predation optimized for scarcity. Dragonfish are not the only hunters here, but they represent a broader pattern. Midwater predators often look exaggerated, almost overbuilt in specific areas, while remaining minimal elsewhere. They invest heavily in capture tools rather than locomotion. In a world with few obstacles and limited prey, chasing is inefficient. Ambush is king. There is also an emotional quality to these predators that is hard to ignore. Their faces look permanent grimaces, jaws lined with spikes that seem excessive until you understand the context. In the midwater, prey items are often close in size to their predators. There is no guarantee of a neat, manageable meal. Teeth that can secure awkward, wriggling prey are essential. Dragonfish also demonstrate how evolution in the midwater favors specialization without redundancy. There is no extra bulk, no unnecessary armor, no flashy displays. Everything serves a purpose. Even their threatening appearance is incidental. The fish is not trying to scare you. It simply evolved in a place where intimidation was less useful than efficiency. The way these predators hunt shapes the behavior of everything around them. Prey animals evolve to minimize detection, reduce movement, and avoid silhouettes. In turn, predators refine their ability to remain unnoticed until the final moment. It is an arms race fought quietly, in inches rather than miles. From a human perspective, dragonfish can seem monstrous. Their teeth look cruel, their eyes stare blankly. But in the midwater, there is no malice, only function. These predators are not aggressive because they enjoy it. They are precise because they have to be. In the end, dragonfish embody the logic of the midwater predator. Do not chase what may never appear. Do not waste energy you cannot replace. Wait, blend in, and when opportunity finally drifts close enough, make sure your teeth leave no room for regret. Finding a partner in the midwater is not romantic. It is not convenient. And it is definitely not frequent. This is an environment where individuals are spread across vast distances. Visibility is limited, and encounters with anything at all are rare. Under these conditions, traditional ideas of courtship and pair bonding start to break down. Evolution responds the only way it knows how, by getting weirdly practical. For many midwater animals, the biggest challenge is simply locating another member of their species at the right time. There are no meeting places, no reliable landmarks, no guarantee you will ever cross paths with a compatible partner. This has led to reproductive strategies that prioritize certainty over comfort. When you find a mate, you do not let go. Ever. One of the most extreme examples of this is parasitic mating, seen in some deep-sea fish. In these species, males are tiny compared to females. Their sole purpose is to find a female and attach to her. Once they do, their bodies fuse with hers, connecting their circulatory systems. Over time, the male loses his independence entirely, becoming a permanent source of sperm. It is less a relationship and more a biological subscription service. From an evolutionary perspective, this strategy makes brutal sense. The female no longer needs to search for mates. The male does not need to worry about finding food or avoiding predators. Both problems are solved in one irreversible decision. It is efficient, if unsettling, and it ensures reproduction can happen whenever conditions are right. Other midwater species use different approaches to solve the same problem. Some release large numbers of eggs and sperm into the water, relying on timing and sheer quantity to increase the odds of fertilization. This method treats reproduction like buying a lottery ticket in bulk. The odds for any single offspring are low, but enough attempts make success statistically likely. This strategy requires precise synchronization. Spawning often occurs in response to environmental cues, such as subtle changes in water conditions or light levels. When the moment arrives, many individuals release their reproductive material at once, briefly filling the water with the building blocks of the next generation. It is chaotic, fleeting, and mostly invisible to anything not directly involved. There are also species that invest heavily in fewer offspring, providing them with more resources from the start. These animals produce larger eggs with more stored energy, increasing the chances that their young will survive the early stages of life. In a harsh environment, starting strong can make all the difference. What unites all these strategies is an acceptance of uncertainty. The midwater does not offer stable conditions for raising young. Currents carry larvae far from their parents. Encounters with predators are unpredictable. Survival rates are low. Reproductive success is measured not by individual stories, but by long-term persistence. Reproduction in the midwater is also shaped by energy constraints. Producing eggs, sperm, or specialized mating structures requires resources. Animals must balance reproductive effort with survival. Invest too much and you risk running out of energy. Invest too little and your genetic line ends. The sweet spot is narrow and constantly tested. The lack of visual cues also affects how reproduction works. Many species cannot rely on elaborate displays or physical contests to choose mates. Instead, chemical signals and simple behavioral cues become important. Attraction is less about appearance and more about detection. If you can find each other at all, that is already a win. From a human viewpoint, these strategies can seem grim or absurd. Permanent attachment, mass spawning into the void, minimal parental involvement. But these approaches are not failures. They are solutions to a very specific problem. How to reproduce when meeting another individual is rare, and survival is never guaranteed. In the midwater, romance is replaced by logistics. Love songs are replaced by chemical cues. Long-term planning gives way to irreversible commitment or statistical probability. Dating, as we know it, would not survive here. Evolution found a way to make it worse, but also remarkably effective. The ocean is often imagined as a stack of separate worlds. The bright surface, the dim middle, and the dark depths below. In reality, these layers are tightly connected, and the midwater is the main reason why. It is not just a place where animals live. It is a highway, a transfer zone, and a living conveyor belt that keeps energy moving throughout the entire ocean. At the surface, sunlight powers the growth of microscopic plants that form the base of the marine food web. These organisms capture energy and turn it into biological matter. But the story does not end there. That energy has to go somewhere. The midwater is where much of it passes through, carried by the movement and behavior of countless animals. As midwater organisms feed on surface-derived resources and then move deeper, they transport energy downward. This happens in many forms: digested material, waste, shed tissues, and eventually entire bodies all sink or are carried into deeper layers. The midwater is the staging area where these transfers are organized, processed, and redistributed. This movement is not random. It is driven by the daily and seasonal rhythms of life in the ocean. Animals respond to changes in light, temperature, and resource availability, adjusting their positions accordingly. As they move, they link environments that would otherwise be isolated. The midwater becomes a zone of exchange, where surface productivity is converted into forms that deeper ecosystems can use. At the same time, the midwater also receives input from below. Materials from deeper waters can be brought upward by currents or carried by animals moving toward the surface. This two-way flow ensures that nutrients are not locked away in one layer forever. The ocean remains dynamic, with resources constantly circulating through its living systems. What makes the midwater especially important is its sheer size. Because it occupies such a large volume of the ocean, even small changes in how energy moves through it can have global consequences. The cumulative effect of millions of daily interactions adds up, influencing everything from nutrient distribution to the ocean's role in regulating the planet's climate. The midwater also acts as a filter. Not all energy makes it to the deepest parts of the ocean. Some is consumed, transformed, or recycled along the way. Predators feed on prey, waste products are broken down, and nutrients are reused by other organisms. This processing prevents sudden surges of material from overwhelming deeper ecosystems, creating a more stable flow. From an ecological perspective, this makes the midwater a critical mediator. It does not produce large amounts of energy itself, but it controls how that energy is distributed. It determines who gets access to resources and when. In this way, it quietly shapes the structure of life throughout the ocean. The connections formed in the midwater also influence evolutionary pathways. Species that move between layers experience different conditions and pressures, leading to adaptations that reflect multiple environments. This blending of influences contributes to the diversity and complexity of ocean life. The midwater is not just a connector of places, but a mixer of evolutionary ideas. Despite its importance, the midwater often goes unnoticed because its work is invisible. Energy does not move with labels or signposts. It drifts, sinks, and circulates, carried by living organisms going about their daily routines. The result is a system that functions continuously without drawing attention to itself. Understanding the midwater as a biological elevator helps clarify why disruptions here matter so much. Changes to the organisms that inhabit this zone can ripple outward, affecting both surface and deep ecosystems. The elevator does not stop abruptly, but it can slow, shift, or malfunction if the balance is altered. In the end, the midwater is the ocean's connective tissue. It links light and darkness, abundance and scarcity, surface and abyss. Without it, the ocean would be a series of isolated layers. With it, the ocean becomes a single, integrated system, powered by movement, transformation, and the quiet labor of life drifting between worlds. For most of human history, the Midwater might as well have been on another planet. Too deep to see, too dark to navigate, and too vast to meaningfully affect. It existed beyond our influence, or so we thought. As technology improved and human activity expanded across the oceans, that invisible boundary quietly disappeared. Today, even the dim middle layers of the sea feel the imprint of human behavior, whether they want to or not. One of the most direct impacts comes from fishing. As surface fish stocks declined, fishing operations moved deeper, deploying nets that sweep through mid-water layers. These nets do not discriminate. They capture target species alongside countless others that were never meant to be caught. Animals adapted for slow movement, fragile bodies, or low-energy lifestyles are suddenly dragged upward at speeds they were never built to survive. Many do not make it back. The scale of this activity matters. Removing large numbers of midwater organisms alters population balances that took millions of years to stabilize. Species that once played quiet but essential roles in regulating food webs are reduced, sometimes without anyone noticing, until the effects ripple outward. The midwater does not have obvious landmarks or charismatic mascots, so changes here often go unseen until they reach more familiar parts of the ocean. Light pollution is another unexpected intrusion. Artificial light from ships, offshore platforms, and even coastal cities penetrates the ocean at night. While it may seem insignificant compared to sunlight, in the midwater, even small changes in light levels can have outsized effects. Many organisms rely on darkness as a cue for movement, feeding, or rest. Altering that signal can disrupt behaviors that evolved around predictable light patterns. For animals sensitive to faint light, artificial illumination can create confusion. It may attract organisms to the wrong depths or keep them from moving when they normally would. Over time, this interference can change how energy flows through the ocean, reshaping interactions that depend on precise timing. Noise is another growing presence. Ships, machinery, and industrial activity add persistent sound to the ocean's acoustic environment. In a place where sound is a primary source of information, this background noise can mask important signals. Animals that rely on vibration cues to detect predators or prey may find it harder to interpret their surroundings. The ocean's concert hall has gained an unwanted non-stop soundtrack. Climate change adds a broader, slower pressure. Warming surface waters, shifting currents, and changes in oxygen availability all influence conditions in the midwater. These changes do not happen uniformly. They alter gradients and boundaries that midwater organisms use to orient themselves. Over time, habitats shift, and species are forced to adapt, move, or decline. Chemical pollution also reaches deeper than we once assumed. Substances released at the surface can be transported downward, accumulating in midwater organisms. These chemicals move through food webs, sometimes concentrating as they pass from prey to predator. Even animals that never approach the surface can be affected by decisions made far above them. What makes these impacts especially concerning is how difficult they are to observe. The midwater does not offer easy visual feedback. There are no bleached reefs or obvious die-offs floating to the surface. Changes happen quietly, detected only through careful measurement and long-term observation. By the time effects become obvious, they may already be deeply embedded in the system. There is also a psychological challenge. Humans tend to protect what they can see. The midwater resists that instinct. Its inhabitants are unfamiliar, its processes subtle, and its importance easy to underestimate. Yet this zone plays a critical role in the health of the entire ocean. Disruptions here do not stay contained. Despite this, the story is not entirely bleak. Awareness of the midwater's importance is growing. Advances in research and monitoring are revealing how interconnected these systems truly are. With understanding comes the possibility of better management and more thoughtful use of ocean resources. The midwater was once considered off the grid, a place beyond human reach. That era is over. Our influence now extends into the dark, shaping environments we rarely think about and almost never see. The challenge ahead is learning how to exist alongside these hidden worlds, without unraveling the quiet systems that keep the ocean alive. For all our technology, diagrams, and confident documentaries, the midwater remains one of the least understood ecosystems on Earth. It fills an enormous portion of the ocean, yet much of it exists only as empty space on our mental maps. We know it is full of life. We know it plays a critical role in the planet's systems. And yet, when it comes to specifics, we are often guessing. Educated guessing, yes, but guessing all the same. The challenge begins with access. Studying the midwater is technically difficult and expensive. There is no surface to land on, no seafloor to anchor to, and no stable frame of reference. Everything is moving, drifting, and changing. Instruments must operate in darkness, under pressure, and often at great distances from human operators. Every observation is hard-won. Even when we do manage to observe midwater life, we are usually seeing only fragments. Short glimpses captured by cameras, blurred shapes passing through lights, creatures that appear once and are never seen again. Many species are known from a single specimen or a fleeting encounter. Their behaviors, lifespans, and relationships remain complete mysteries. Classification adds another layer of uncertainty. Traditional taxonomy relies on physical specimens, but collecting midwater animals intact is notoriously difficult. Fragile bodies are damaged by nets or pressure changes. As a result, some species are described from partial remains or observations alone. Others remain unnamed because there simply is not enough information to place them confidently within existing groups. There is also the issue of scale. The midwater is vast beyond everyday comprehension. Even extensive research campaigns cover only tiny fractions of it. Discovering a new species here is not like finding a needle in a haystack. It is like finding a needle in an ocean-sized haystack that is actively trying to move out of the way. Our lack of knowledge is not limited to species identification. We know surprisingly little about how many midwater organisms live where, how populations fluctuate over time, or how different species interact. Food webs are inferred rather than mapped. Life histories are pieced together from indirect evidence. The big picture exists, but many of the details are still missing. Technology is slowly improving our view, but it brings its own limitations. Cameras show us what happens in front of the lens, not what happens beyond it. Sensors collect data, but data does not automatically become understanding. interpreting what we see requires assumptions. And assumptions can be wrong. There is also a philosophical discomfort in admitting how much remains unknown. Humans like narratives with beginnings, middles, and ends. The Midwater refuses to cooperate. It is a place of gradients rather than boundaries, probabilities rather than certainties. Each answer tends to generate new questions faster than it resolves old ones. And yet, this ignorance is not a failure. It is an invitation. The Midwater represents one of the largest unexplored biological frontiers on the planet. New discoveries here are not rare. They are expected. Entire categories of life likely remain undocumented, quietly existing beyond the reach of our current tools. There is something humbling about that. In an age where satellite images can resolve objects on land in fine detail, the ocean still holds secrets at scales that matter. The Midwater reminds us that the planet is not fully mapped, not fully understood, and not fully under control. The idea that unseen species might be judging us is, of course, a joke, but it reflects a deeper truth. The Midwater operates independently of our awareness. Its inhabitants do not care whether we know their names or understand their roles. They continue drifting, feeding, reproducing, and interacting according to rules shaped long before humans appeared. Perhaps that is the most important lesson the Midwater offers. Knowledge is not guaranteed. Understanding requires patience, humility, and a willingness to accept uncertainty. The darkness is not empty. It is simply waiting. Full of life we have yet to truly meet. When people imagine alien worlds, they tend to look up. They picture distant planets, strange skies, unfamiliar gravity, and life forms that defy imagination. Yet the most alien environment we know is not light years away. It is right here, beneath the hulls of ships, under the paths of migrating whales, and below the glittering reflection of the night sky on the sea's surface. The Midwater is Earth's largest living space, and it remains profoundly unfamiliar. This realm does not have mountains or forests or cities of coral to orient the eye. It is a place defined by absence. No solid ground, no stable landmarks, just water stretching in all directions, layered by pressure and darkness. Life here exists in suspension, unmoored from anything we would recognize as a home base. That alone makes it feel otherworldly. What is remarkable is not just that life survives here, but that it thrives. Entire communities drift through this vastness, interacting, feeding, reproducing, and adapting in ways that make sense only under these conditions. The Midwater is not a barren gap between surface and seafloor. It is a complete ecosystem, operating by rules that are invisible unless you know how to look. Seen this way, the Midwater challenges our ideas about habitability. We often define livable environments by what they offer us: solid ground, light, warmth, and clear boundaries. The Midwater offers none of those things, yet it supports an astonishing diversity of life. It suggests that life is far more flexible than our instincts assume, capable of building entire worlds out of what seems like nothing. There is also something quietly humbling about how the Midwater coexists with us. Ships pass overhead, unaware of the intricate lives unfolding below. Satellites track ocean color and temperature, while beneath that data lies a living volume that resists easy measurement. The Midwater does not announce itself. It does not demand attention. It simply exists, vast and busy, regardless of whether we notice. This disconnect shapes how we think about the planet. We tend to define Earth by its surfaces, by the places we can stand, build, and see. But most of Earth's living space is not on land. It is suspended in water, in darkness, governed by physics and biology that feel unfamiliar because we did not evolve within them. The Midwater reminds us that our perspective is limited. It also reframes the idea of exploration. We often talk about space as the final frontier, yet we have explored only a fraction of the ocean's interior. The Midwater is not just unexplored territory, it is unexplored volume, a three-dimensional world that dwarfs the spaces we usually map and name. Every descent into it is less like a hike and more like entering a foreign atmosphere. There is beauty in this realization. The Midwater does not need to be conquered or fully understood to be meaningful. Its value lies partly in its mystery. Knowing that such a vast, complex world exists alongside our own expands our sense of what the planet contains. It makes Earth feel bigger, stranger, and more alive. At the same time, this awareness carries responsibility. When we recognize the Midwater as a living space rather than empty water, it becomes harder to ignore the consequences of our actions. What happens at the surface does not stay at the surface. The boundaries we draw are conveniences, not barriers. The Midwater absorbs, responds, and adapts, but it is not immune. In the end, the Midwater invites a shift in perspective. It asks us to imagine life beyond our usual reference points, to accept that entire worlds can exist without scenery, without sunlight, and without our participation. It reminds us that Earth is not just a backdrop for human activity, but a layered, dynamic system filled with places we are only beginning to appreciate. The most alien world is not waiting to be discovered among the stars. It is already here, drifting silently beneath our boats, carrying on with its business in the dark, vast, and quietly extraordinary middle of the sea.